separate the variables again, or isolate them, however you want to say it. So it's going to be, let's see, it's going to be d psi 0 over psi 0 equals minus m omega x over h bar dx. Make sure I get that right. Yes. All right, how do I solve that?
Integrate both sides.
Integrate both sides. Is it a definite or indefinite interval?
Indefinite.
An indefinite interval, so on one side I've got to make sure I carry around the c, right? So what's the interval on this side?
Natural log of psi
So
0.
it's log psi 0, and what is that equal to? Minus m omega over h bar over x squared over 2
Plus c.
plus c. How do I solve that?
Both sides.
Okay, so e to the minus m omega x squared over 2 h bar, right, times e to the c equals psi 0, or psi 0 of x equals some constant, we'll just say some constant c, e to the minus m omega x squared over 2 h bar. Okay. Who cares? What did I just do?
You solve for psi 0.
Okay. I just solved for psi 0, which is the ground state, stationary state of the harmonic oscillator. All right.
And p psi of n, you just multiply the exponent times n.
Okay, so look, I think, David, you're on the right track. So our goal, remember our goal, and we solved differential equations before. Our goal was to solve this messy differential equation, right? But what we did is we used these raising and lowering operators, and we just solved for one state, the ground state. Right? So we didn't solve for them all. We solved for one. But now can I solve for another one?
Yeah.
How?
Raising operator.
Now you just use the raising operator. So how do you solve for psi 1? Psi 1 of x equals?
Raising operator times psi 0.
Yeah, raising operator times psi 0. All right, and what's the raising operator? Well, it's this thing. It's 1 over square root of 2 h bar m omega, right? And then it's going to be minus I times I, and what do I mean minus? I h bar partial with respect to x, or let's do the total derivatives again, d by dx, right? Plus m omega x, all that times
Psi 0.
psi 0. Now can you do that? Is that hard?
No.
First we have to normalize.
Oh yeah, so I agree completely. Yeah, I haven't, Alamar wants to normalize and you are 100% right. I'm going to leave that to the end though, okay? But if you do this, so this comes out to be equal 1 over the square root of 2 h bar m omega, and then what is this? This is a plus times a minus, so minus h bar d psi 0 dx plus m omega x times psi 0. And look, can I take the derivative of psi 0 with respect to x? Can you all do that? Is that hard to do?
No.
All right, can you multiply m omega x times that?
Yes.
Is that hard to do?
No.
Okay, then in the end, have I solved for psi 1 of x?
Yeah.
Yeah. All right. So I solve for psi 1. Can I solve for psi 2 of x?
Just times that one.
Okay, so psi 2 of x, check this out. How about if I did it as a plus dagger, you can write it like this, times sine 1 of x. But this equals a plus dagger psi 0 of x. Right? Or in general, psi n of x equals
A plus dagger to the n, psi 0.
times psi 0 of x. That's it. All right. Now, it's important that Griffiths goes on to calculate the normalization. All right, Elamar, this is what you were asking. And so here are the normalized. Normalized.
Did you do that just to get C out of your sign?
Yeah, we got to normalize for C, to be consistent with the Born interpretation. Is that psi n of x's equal 1 over the square root of n factorial a plus dagger to the n psi 0 of x. Okay, these are our normalized stationary states of the harmonic oscillator. So have we solved for the stationary states of our original problem? Yeah. Have we done it any easier than the analytical method of solving that differential equation? You might argue no. All right. But this is a very general technique, and after all the stuff that I did in the middle, after you understand the stuff in the middle, you no longer have to do the stuff in the middle again. You just use this generalized technique of raising and lowering operators. Right? So, had we known all the stuff in the middle, all the algebra in the middle, and we simply knew this idea about a raising and lowering operator was, then I could have just solved the differential equation. So, for example, if I had known everything in the middle, I could have just gone right over to here, right?
But you wouldn't have known how it connects.
Right, but I wouldn't have, but if I did, if I put in the work so I know the connection, I understand the trick. Once I know the trick, and I use this, and that's the whole idea. One further thing is we have to know the energies. All right, so we have to know the eigenenergies. So let's see how the eigenenergies go. So we have the normalized eigenfunctions. The eigenenergies go like this. So for example, for E0, so the eigenenergies, okay, the eigenenergies go like this. Let's look for E0, the ground state energy. So how about this? The Hamiltonian for the H oscillator times psi 0 equals E0 times psi 0. Let's use this form of it. A dagger plus A dagger minus plus H bar omega over 2 times psi 0 equals E0 psi 0. Okay? So I'm using the second formula, the first formula we had. Sorry, wait a minute. A plus, A minus. I have this wrong. Oh, no, I have this right there. Yeah, I'm right. So A plus, but I had written it
You have to
again.
multiply by h bar omega. So,
Yeah.
A plus A minus.
Yep, this works. This is right.
But you gotta multiply A plus A minus by
By
h
H
bar
bar
omega.
omega. Thank you. All right, and H bar omega there. All right, so then I end up with H bar omega, A dagger plus A dagger minus on psi 0 plus H bar omega over 2 times psi 0 equals E0 times psi 0. And then what happens to this whole term?
It goes away.
Why?
Because you're raising and lowering the thing.
No, you lower first, it goes to zero.
Because
Yeah,
you're
and that
lowering
goes to
first.
0, yeah, yeah. So, oh, wait a minute.
No.
So what happens to this? This goes to 0,
Then you bring it back up to 1.
1, side 1.
Can you raise zero? The number is zero. You're applying an operator to a number zero.
That's right, so it goes to 0. Wait a minute, but we're doing it over here.
That's just H omega size 0, right? 'Cause you raise it and lower it. Size
Don't,
Yeah, so what am I missing here?
would the operators cancel or no? Or they just,
You have to operate first to the right. So the first thing it hits is size zero, that becomes zero, then you operate on zero.
Oh yeah.
Oh, yeah,
you
yeah, that's
can't-
it, yeah.
And
Like,
yeah,
I can operate A plus on 0.
Which you get to side 1.
Yeah, because check it out, look, so here we can do it by example. It's clear that I can do A plus on size 0,
Mhm.
right? But let's do this, let's do A plus, let's do A plus on A minus size 0. That's going to be 0, so this is going to be A plus not on size 0, it's going to be on 0, which equals, put in all this machinery up here, 1 over the square root of stuff, but then it's going to be the derivative with respect to x plus m omega x all times 0. And what does that give me? 0. All right, so it doesn't raise 0 back up to the ground
So
state.
once you get-
here.
under the ground state, you're just
Once you get
Done.
below, yeah, yeah. So this literally goes to 0, and not literally, it does go. It equals 0. All right. And so what we're left with is h bar omega over 2 times psi 0 equals E0 times psi 0. Okay.
once you drop to 0, you fall
So-
into a black hole, you just never come out again.
Well, this is getting kind
But
of funky.
so E0 is basically half a chunk of the energy.
Oh, so you nailed it. So the ground state of every harmonic oscillator, right, the lowest energy it can go, right, if it's there, the lowest energy it can go is a half a chunk of quanta, which is very funky, right?
Let's do that.
How do you do that? All right. You know, real quick, once you have this, what is E1 then?
It's H omega size 0. It's double.
No, it isn't. You have to.
No, it's wrong.
You're in the
You
right
have to
idea.
do E0 times A dagger plus. Like A dagger
No,
plus.
let's just think about it. The whole argument that we made up when we looked at it in an eigenvalue problem is we found En, right, plus an H bar, plus a full H bar omega, and we said that was plus 1 whole quanta to get to the next
So
energy.
E1 would be 1
So this would be,
1.5 chunks.
what would be 1.5 chunks? So it would be H bar omega plus H bar omega over 2. Right? Or would equal, well, let's see, H bar omega n plus a half. Right? So e to the n, so e to the 1 equals this, or e to the n equals H bar omega n plus a half. Where it says for each station, whatever the stationary state is, that's how many chunks of quanta I have, plus a half, where the half came from the ground state energy.
So you could say that like the amount of energy in the ground state is half of that of the.
Yeah, I'm saying it's very funky, and I don't have an answer to that.
Okay. So what are you saying? It's half of though. It's half of.
Half of the fundamental chunk of energy. It's the only thing that has the half a chunk of energy.
So in the total energy in the ground state, out of that, what's half of it is what?
It's half the lowest possible energy you have.
So if you want to think about it, it's half a photon, which doesn't make sense,
Oh, okay.
right? So, you know, we're now talking about quantum mechanics, where everything comes in chunks of h bar omega, or h times frequency.
Yeah.
All right, and what we've just found out is that for harmonic oscillators,
It comes in half the chunks.
Well,
Just
it
the
doesn't.
ground
There's
state.
just half, there's an
Just
extra
the
half a
ground
chunk hanging
state.
around.
That's it. That's the way to look at it. That the ground state of harmonic oscillators has half a chunk of energy, and then everything else after it comes in the one chunks.
How often you have a ground state or harmonic oscillator?
Okay, so how often you're in the ground state of a harmonic oscillator? Right? Well, if you have electromagnetic waves, right,